Okay, so we're moving on to section 10.2. We'll come back and take care of 10.1 later, but first we're going to take care of 10.2. And we're going to be talking about plane curves and parametric equations, section 10.2. Okay. So to motivate parametric equations, here's an example. A rifle is on top of a 64-foot tall building, pointed horizontally. At the instant it is fired, a bullet is dropped from the building. Which one will hit the ground first? The bullet that was fired or the bullet that was dropped? Now, for some reason, people's intuition here tells them that the bullet that was fired will hit the ground first. But it turns out that the horizontal component of motion and that the vertical component of motion is independent. They're independent of each other. And so we can describe the fired bullet with not just one equation, but with two equations that sometimes makes things a little bit easier. So for example, if the bullet leaves the barrel at 1,000 feet per second, how far from the building will it hit the ground? So rather than trying to find one equation to describe the motion of the bullet, we can find two equations. So since the bullet is fired at 1,000 feet per second, how far it will travel horizontally is just a simple distance equals rate times time. So x of t, how far it will go horizontally, is just 1,000 times t, however many seconds. Now, to find y of t, we can start with y double prime of t, because that's the acceleration due to gravity. The acceleration due to gravity is negative 32. Feet per second squared. We can integrate that to find the velocity, and that will give us negative 32t. And then we can integrate that to find the position. I'm sorry, y prime of t is negative 32t plus c, but because it was dropped, c is 0. We could then integrate that to find the velocity, the position, which is then negative 16t squared plus some constant, but it was dropped from 64 feet above the ground. So the constant when time is 0, the height is 64. So how high it is off the ground is negative 16 t squared plus 64. And so that formula was a lot easier to find. We could find it using the calculus than it is going to be to find the formula for the actual trajectory. The actual trajectory in the xy plane is going to look like this. This is x, this is y, the bullet is fired, it's going to follow a parabolic path, and there it is, right? So, but rather than just having one equation that relates x and y, we have two equations. One that relates x, how far the bullet goes horizontally. That was pretty easy. It's just a 1,000 t, and how far it drops. And that's y of t, which we found not so bad. Just finding a couple antiderivatives, very simple. But now at every particular time, we put the time into this formula, and that tells us how far over we've gone. We put the time into this formula, and that tells us how far up we are from the ground. And so then those two combine to give us a x and a y coordinate, a position of my particle, or of my bullet. But now we can answer the question, how far from the building will it hit the ground? So how far from the building? We want an x coordinate. We want this x coordinate right here. But What's special about that x coordinate is that the y value is 0. So we can figure out what's going to make the y value 0 in this formula. And then we add 16t squared. Divide by 16. Square root. It's going to take 2 seconds to hit the ground. Okay, now once we know that it takes 2 seconds to hit the ground, we can then figure out how far we've gone by using our horizontal motion formula. X of 2 is 1,000 times 2. So it will hit the ground 2,000 feet from the building. Okay, so let's go over a definition. If f and g are continuous functions of t on an interval I, then the equations x equals f of t and y equals g of t are parametric equations, and t is the parameter. The set of points x, y obtained as t varies over the time and over the interval I is the graph of the parametric equations. Taken together, the parametric equations in the graph are a plane curve denoted by C. Just some vocabulary, some words we're going to use. Okay. Graph the curve described by the parametric equations below. Okay, so when you're graphing parametric equations, several ways to do that. One way to do that is to make a table of values. Except you're plotting the points x, y, and to find your points, you need values of t. So you can put in some, so t goes from 0 to 3, so you can just put in those integer points right there. We can put in 0, 1, 2, and 3. And when you put in 0 into the x formula, you get negative 3. And when you put in 0 into the y formula, you get 1. When you put in 1 into the x formula, you get negative 2. And when you put in 1 into the y formula, you get 4. When you put 2 into the x formula, you get negative 1. And when you put 2 into the y formula, you get 7. And when you put in 3, you get 0. And when you put in 3 into the y, you get 10. And this is what you plot. All these are plotted on the xy plane. And so then you get negative 3, 1. 1, 2, 3, 1. Negative 2, 4. 1, 2, 1, 2, 3, 4. And negative 1, 7. 1, 2, 3, 4, 5, 6, 7. Two, 3, 4, 5, 6, 7. Missed it. And 0, 10. Okay, and I'm missing the negative 2, 4. 1, 2, 1, 2, 3, 4. For some reason, this was only defined for the interval from 0 to 3, so we start here and end here. The graph is a line, and the arrows indicate the direction. So one of the nice things about parametric equations is not only do you have the points, you're also able to give this a direction. Your graph started here at 0 and ended at the point negative 3, 1 and ended over here at the point 0, 10. And that is the entire graph. Okay. Both the x and the y are linear, so shouldn't be a surprise that the graph is a line. But another thing that you can do is you can eliminate the parameter. So the top formula tells you that your x is equal to t minus 3. You can then add 3 to both sides to get the t is equal to x plus 3. And then in your second formula, you can go and you can substitute in x plus 3 in for x, and you get 3 times x plus 3 plus 1, which is 3x plus 9 plus 1, which will then make that a plus 10. And you see that the rectangular equation for this, the regular equation, is y equals 3x plus 10. It's just a line. Okay. Graph the curve described by the parametric equations below. X equals cosine t, y equals sine t, and your t values vary from 0 to 2 pi. So we have t, x, and y. We're only interested in this in the interval from 0 to 2 pi. So in trigonometry, we learned to use the quadrant angles when we were graphing this. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0, and cosine of 2 pi is back to 1. For the sine function, sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And sine of 2 pi is 0. And so then we get the points 1, 0, 0, 1. Let me go ahead and give this a better scale. Let's make the scale so that each 4 is worth 1. 1, 2, 3, 4, that's 1. 1, 2, 3, 4, that's 1. And so then we have 1, 0, 0, 1, 1, 2, 3, 4, negative 4, 0, and 1, 2, 3, 4, 0, negative 4, and then we're back to 1, 0. It's not obvious what this graph is. So if we try to eliminate the parameter, rather than solving for t like we did in the last problem, to eliminate the parameter here, we use a trig identity that the sine squared of theta plus the cosine squared of theta is always equal to 1. So if we square both sides of this equation, we get that the cosine squared of t is x squared. And if we square both sides of this equation, we get that the sine squared of t is equal to y squared. And then if we add these two equations together, we get that the cosine squared of t plus cosine squared of t plus the sine squared of t is equal to x squared plus y squared, but the left side is 1. And you should recognize that equation, 1 equals x squared plus y squared, as the equation of a circle. And so this is exactly a perfect circle. And the direction that it goes is it goes in this direction. We started at this point, went to this point, went to this point. We're just going to keep going around and around. And there we go. Graph the curve described by the parametric equations below. X is equal to the secant of t, y is equal to the tangent of t. But we're only interested in this in the interval from pi to 3 pi over 2. Notice that we're not allowed to use 3 pi over 2. Tangent is the sine over the cosine, and with the sine over the cosine, we have a vertical asymptote there, and so we're not allowed to use the 3 pi over 2. So if we start at pi, secant is 1 over the cosine. Cosine of pi is -1. The reciprocal is still -1. The tangent to pi is 0. And then we'll go to pi plus pi over 4, which is 5 pi over 4. And then the secant is the square root of 2. And the tangent in quadrant 1, in quadrant 3, the tangent is positive. And so then we get +1. And then 3 pi over 2, we don't have anything else. So we only have these 2 points. And so we're going from, we're starting here at -1, 0. -1, 0. And then 5 pi over 4, that should be a negative. Right? Negative the square root of 2, 1. Square root of 2 is there. Not a whole lot of information by which to make this graph. Negative the square root of 2, 1. Why are you doing Okay. So it's kind of hard to see that. Okay, so again, we could better make a description of what's going on here by eliminating the parameter. And so to eliminate the parameter, we can use the fact that the secant squared is equal to the tangent squared plus 1. Okay, so then if we square the secant of t is x, so the secant squared of t is x squared. The tangent squared of t can be replaced with y squared, and then plus 1. And we can rewrite this as x squared minus y squared equals 1. You should recognize that as a hyperbola, but we're only interested in angles from pi to 3 pi over 2, and so then that means we're only going to get this branch of the hyperbola. And it goes on forever because of this asymptote, right? And so there we go. How we get that. Okay. Now, from time to time, we're going to want to take a rectangular equation, and we're going to want to write it in parametric form. And so when one of the variables is by itself, so for example here y is by itself, then this is going to be pretty easy because we can just let x equal t, and then we can substitute in for x the t and get t cubed plus t plus 1. Now your calculator has a parametric function mode where you can put in your equations in parametric mode, and then we can do things that we couldn't normally do with the graphing calculator. So it says write the inverse of y equals x cubed plus x plus 1 using parametric equations. Okay, so using parametric, so using the inverse of this equation, is x equals y cubed plus y plus 1. And we can't plug that into the calculator to see what the graph looks like. It's easy enough to switch the x's and y's. But now we can parameterize this by just letting y be t, and then x is t cubed plus t plus 1. And we could plug this into the calculator and look at this function as well. Okay. In exercises 5 through 22, sketch the curve represented by the parametric equations, indicate the orientation of the curve, and write the corresponding rectangular equations by eliminating the parameter. There's no formula for this, no easy way to do this, and it just takes a little bit of practice. We don't always need to solve for t. If you notice here, for y, we have t to the 4th, which over here we have a t squared. So then we have y equals t squared squared plus 1. And so then we can take this equation and solve for t squared. So t squared is x divided by 2. And so then we can substitute the t squared with x divided by 2 squared plus 1. And so then this will be x squared over 4 plus 1. And that's just the parabola. Now, when you look at your formula for x, you can see that no matter whether you put in a positive value or a negative value for t, your x is always going to be positive. It could be 0 by putting in 0, but it's never going to be negative. So this you should recognize as a parabola, but you're not looking at the whole parabola because you're only looking at the part of the parabola with positive x values. So your curve is actually going to look like this, and it's going to go in this direction. Now, the direction is probably easier seen by, actually it goes in both directions, making a table like we did before. T, x, y. If t is 0, then, sorry. The vertex is up here at 1. It's not at 0, 0. If t is 0, then x is 0 and y is 1. If t is 1, then x is 2 and t is 2. And if t is 2, then x is 8 and y is 16. I'm sorry, 17. And so then you can see that you start here at 0, 1, and then go to 2, 2, and then go to 8, 17. So your direction is in this direction. But if you look at the negatives, negative 2, negative 1, when you put in negative 2, you get 8 for x, and you also get 17 for y. And so now you're actually over here. So depends the direction, it actually goes both ways. From the negative, it's coming in like this, and then from the positive, it's going up. So you need to be careful with that. But you're still only going to get half of the parabola. When you put in negative 1, you're going to get 2, and you're going to get 2. And when you put in 0, you get 0 and you get 1. Not going to make the table. I've already done that for you. Actually, let's just go ahead and quickly make the table. Your parameter now is theta. It doesn't have to be t. Your x and then your y. You're looking at these trig functions, so it should make sense to put in the quadrant angles. 0, pi over 2, pi, 3 pi over 2, and 2 pi. When you put in 0, you're going to get 3 for your x, 0 for your y. When you put in pi over 2, you're going to get 0 for your x and 7 for your y. When you put in pi, you're going to get negative 3 for your x and 0 for your y. When you put in 3 pi over 2, you'll get 0 for your x and negative 7 for your y. And when you put in 2 pi, you're back to where you started, 3, 0. And so then you get these points. And it's not a nice perfect circle because the coefficients are different, but it looks like it was an ellipse. And this is your direction, right? To see that this is an ellipse, again, the cosine of theta is x over 3. And the sine of theta is y over 7. And the cosine squared, x over 3 squared, plus the sine squared, y over 7 squared equals 1. So x squared over 9 plus y squared over 49 is equal to 1. And you should recognize that as the equation of an ellipse. Center at the origin, major axes of length 14, minor axes of length 6. So definition of a smooth curve. Curve C represented by x equals f of t and y equals g of t on an interval I is called smooth when f prime and g prime are continuous on I and is not simultaneously 0, except possibly at the endpoints on I. The curve C is called piecewise smooth when it is smooth on each subinterval of some partition of I. So now we can define what smooth is. And smooth is just defined as long as your derivatives are continuous and not simultaneously 0. Okay. So in exercises 51 through 54, find two different sets of parametric equations for the rectangular equation. So again here we have y as a function of x. So very easy to just let x equal t, and then y will equal 4 over t minus 1, because wherever x is t. Okay. Now, but it says find two different sets of parametric equations. So that's one. So here's one parametrization of this curve. We could also let y be t. And then, but then we have to figure out what to substitute in for what's the parametric equation for x. Well, to do that, we can just take our formula and solve for x. So then x minus 1 times y will equal 4. So then x minus 1 will equal 4 divided by y. So then x will equal 4 divided by y plus 1. But then we know that y is t. So x is equal to 4 divided by y. I'm sorry, 4 divided by t plus 1. And this is our a different set of parametric equations. So again, not to make things complicated, no need to overcomplicate things, but we can let x equal t, and then once we do that, y is just t squared because x can be replaced with t. And there are your parametric equations. If I try the same thing that I did last time, then when I go and try and solve for y, it's going to be a little confusing because of the square root. So here's another thing we can do. There was no reason why we let x equal t other than it was easy. So we can let x equal t minus 1. And so then y, I just go to my formula and I replace x with t minus 1. And these two parametric equations are the same. They'll have the same points. But the tables will look different, right? But the curves should be exactly the same. The points on there will be the same, but you will get different points. You won't get the same point at the same t value. Okay. In exercises 55 through 58, find a set of parametric equations for the rectangular equation that satisfies the given condition. So we want to parameterize this line, but we want to parameterize it in such a way that when I put in -1 for t, the point I get is -2, -7. So again, we want x to equal some function of t, so the easiest function is to just let t be there. But when I put in -1, I want to end up with -2. So if I just subtract 1, then when I put in -1, -1 minus 1 will give me this -2. But now the y is 4 times the x, so 4 times the t minus 1 plus 1. So this is 4t minus 4 plus 1 minus 3. And so now when I put in the -1, 4 times -1 is -4 minus 3 is -7. So this is the correct parametrization that makes it so that when t equals -1, we get the point -2, -7. Okay, so here's your homework for this section. This will be due next week on the 30th of April. And that is it.